Good morning, everyone. Thank you for joining us today. So my name is Jesus Barraza. I'm the Director of Telecoms at Neo4j, and I would like to use the next half hour to talk about how Neo4j graph databases are being used in the telecoms industry by going through a number of key use cases. And I would also like, especially for those of you who are new to graphs, to be able to also get an intuition of the value that graphs add to your solutions. So that's my plan for today. But let me start with some figures that I believe give an idea of the level of understanding and where we are in terms of adoption. I was saying that the level of understanding by some of the leaders in the telecoms industry. So if we look first at the carriers, or the top carriers globally, we see that 2 out of the top 3 are already using Neo4j to build critical solutions. But if we look at also telecoms equipment vendors, we see that also in the top 5, 3 of them are already embedding Neo4j in some of the key products. So I think that's pretty significant footprint in the industry, as you can see. And if we ask ourselves why, I would say that, well, obviously these big companies are becoming aware of the incredible value in looking at your data in terms of connected data points. So sometimes, I mean, we realize that there's more value in the connections between data points than there is in the data points themselves. So this way of looking at data brings a lot of value, and it can be a very a differentiator, as we're aligned with some of the key analysts like Gartner, as you can see. But if I want to be a bit more specific, I think these the use cases that we're going to be talking about in the telecom space, and this right here is intentional. So if I was asking myself which are some key elements in telco solutions that are common to most of them, and that graph databases address in a particular way, I would think of 3 of them, and one of them is complexity. So we're looking at a really complex model. So you probably most of you are familiar with some of the more popular graph use cases, like I'm thinking here of the Panama Papers, or something like recommendations, where we model individuals, we model customers, we model products, and we model connections between them. So that's I'm not saying that's simple, but it's nothing compared to if you think of a multi-layer network topology. So it's connected devices that depend on other layers. So the complexity is significantly higher, and we need a model that can accommodate this complexity in a natural way without introducing additional accidental complexity, as we like to call it, like is the case with the relational data model. So that's one of the features that the graph model, this richness, this expressiveness, will be able to capture the complexity that's required in the telecom space. The second one is flexibility. That's not exclusive of telecoms, but it's especially important. So we're in an environment where there's multiple vendors, multiple technologies changing very frequently, and being able to accommodate these changes, to be dynamic, to be flexible, to be agile, it's crucial, and that's another thing that the dynamic graph model will address. And finally, the third one is performance. Performance is critical because we see that in a large portion of the use cases, we will be looking at automated processing. So I've mentioned before cases like the Panama Papers, where maybe an investigative journalist will be exploring a graph, looking for unexpected connections. This is a case where we are visually exploring a graph, which is something that graphs lend themselves naturally to. But if we shift to telecoms, most of the times we're going to be talking about systems issuing a request to a graph database, expecting the graph to run a complex traversal and returning an answer that they can act upon in a matter of milliseconds. So in this scenario, performance is going to be crucial, and the graph native characteristic of Neo4j in particular is going to be crucial. So this native storage and processing is going to be a key element. So I think these 3 characteristics and these 3 requirements explain in a way the level of adoption and the level of realization by these leaders in the telecom space, and in terms of adopting graph technology. So I'll talk about a bit more about graph native later on in the presentation, but yeah, I was saying that graphs are a transformative technology, but graph thinking, this idea of looking at your data from the point of view of how it is connected and how the traversal, the exploration of these connections brings value is crucial. And I wanted to run some kind of example or experiment to show that to you. I was mentioning before that I would like you to live with this intuition of how graphs bring immediate value. And I was thinking of a simple example, but I wanted it to be relevant in the context of the telecom. So I thought of dependency modeling. Dependency modeling is huge, because if you think of complex services that depend on components, the components depend on infrastructure elements. So modeling this dependency is super important for a number of use cases. I'm thinking here of impact analysis, troubleshooting, planning, provisioning. So let me run these experiments for you. So look at this data set. This, you can think of it as the simplest abstraction in terms of representing dependency. So it's a simple table where you see elements that depend on other elements. So I was saying these can be logical connections in a network topology that depend on physical infrastructure, that can be services that depend on other services, that can be products that depend on, you name it. So each record here represents something depending on something else. So A depends on B, A depends on C, C depends on H, etc., etc. So that's a way in which we've been representing data for ages, which is basically the relational model. But I'm going to challenge you here to answer a question in a short space of time. I'm going to give you 4 or 5 seconds. And here's my question. So does A depend on F? Right, so I'll give you 4 or 5 seconds. Maybe some of you have the answer. I don't think it was an easy thing to run, but now I'm going to ask you to look at exactly the same data, but this time as a graph. So what I've done is now elements are represented by nodes in the graph, and the dependencies are explicit connections between elements, as you can see. So, well, you can now see the answer for the previous question. So there's no dependency between A and F. So those of you who thought there wasn't, you were right. But as I say, it was not an easy thing to run, especially in 5 seconds. But let me rerun the challenge and ask you again another question. And this time, I'm sure you're going to need a lot less. So does A depend on M? Not even going to give you 2 seconds, because I'm sure you've been able to give me an answer. So of course this is just an experiment, but the point that I want to bring is the fact that a tabular representation is not optimal at all to model things like dependencies, right? So what you see on the left-hand side and what we've been doing is actually doing what relational databases do. So we scan the table for dependency between an element and another, and then we re-scan it to see indirect dependencies and so on and so forth until we get eventually to the dependency that we're looking for. So this is, and you can see on the left-hand side some sort of SQL that would run this kind of process, like a number of self-joins. Whereas on the right-hand side, we see the same data, this time represented as a graph. And this is a more adequate representation for this kind of question. So we can express it. You see there is Cypher, is the query language for Neo4j. I'm not planning to give a tutorial on it, but you can probably follow that. What we're doing is matching, trying to find an element by name. We find E, and then we follow the dependency chain, right, all the way to M eventually. And what we mean by this asterisk is that this dependency can be direct or indirect. So you might need to follow a number of hops in the graph. So it's a way more concise, more compact, easier to understand, and way more performant, as we're going to see. So I hope that made you feel like a relational database trying to solve a graph problem by doing this exercise. And it can get even more complicated. So let me present another example, which is the detection of single points of failure. So a single point of failure is a component in a system or an element in a complex, we can say, a service on which all the service or the system depends. So basically, if this element goes down, this single point of failure goes down, the whole service goes down with it. So let's look again at the same data set, and I've marked in red M. And I've done that because, well, let's start from E actually. So we can see these dependencies as some way of providing redundancy for a service. Let's think E is a service that's critical, and we have a an SLA that basically we have to provide 24/7 service, and by having a dependency on F and G, that provides redundancy in the sense that if F goes down, we still have G. So we can think of this model, we can interpret it in this way. So that gives us peace of mind in the sense that we think it's protected, we're safe. But if we analyze the graph, we obviously see that there's indirect dependencies between both G and F and M. So essentially what happens is that if M goes down, both F and G are down, and therefore the service becomes unprotected. So these indirect dependencies, again, as we were saying before, are not easy to detect, and this is a single point of failure, which is a complex problem. It's not an easy one, especially in complex systems like this one, complex network topologies or complex services. So what's brilliant is that in a graph, this is, as you can see, it's easy to describe with a pattern because it's a loop, right? So let me again describe it in terms of or using Cypher. So what you see here is we have an element X and a single point of failure. Basically, it's a more than one path, more than one chain of dependencies that terminate in the same single point of failure. So this expression describes the path, describes the pattern, and if we run it against the graph database like Neo4j, we would get all the matches, and here is just an example of this execution. But these sort of complex problems are way easy to express and way more performance in a graph database. So think of it, if we go back to our tabular, I mean, I'm not going to ask you to do it. I mean, that would be quite a bit of time, but it would be way more complicated, right? Okay, well, anyway, enough experiments. You can think of many more questions that we could ask in an easy and natural way with a graph that would not be easy at all with a non-graph representation. Things like, which element in your system or in your network needs additional redundancy because it has too many things depending on it, and this dependency can be direct or indirect. So again, we're facing the same kind of problem. Or if we analyze it the other way around, which having a list of elements failing or affected by some kind of situation, is there another element in your network? Is there another element in your systems that can explain this simultaneous failure? Again, this genuinely a graph problem that's easier solved in a graph. But yeah, I was saying that let's stop with the experiments here, and let's go back to adoption. So I was talking before about carriers, a bit big telco companies that we can probably extend to also communication service providers and maybe cable and satellite companies as well, as you can see in that list. But there's not just carriers and equipment manufacturers, equipment vendors in the telecom space. There's also software and services companies like HP and Zenos, as you can see, that are using Neo4j. But let me explain what some of these the use cases, how are they using graphs. And I've tried to categorize that in a number of areas. So these are the ones that I've come up with. So there's Internet of Things, there's a network to be managed. There's the typical BSS and OSS orchestration. But there's also interesting areas like compliance and fraud analysis. Let me talk briefly about some of them. So in OSS, basically OSS, operations and support systems, that's the part of the systems that are used to manage networks, and OSS systems are typically used by network planners, service designers, operations, the NOC. And we have classical problems there around service assurance, things like impact analysis, basically troubleshooting your network. So impact analysis, root cause analysis, we're going to talk a lot more about that later on. But there are also other interesting areas like unified inventory. So being able to come up, this is kind of I wouldn't call it MDM, but probably single view of your network. So if you think of it, you can have information coming from element managers, from discovery tools, from inventory systems, and and sometimes that misaligns. So being able to provide a unified view is a very powerful thing that you can run in a graph. Also in the design and planning areas, we have customers using that. But let me talk a bit more about the service assurance side, and this simple diagram on the right-hand side kind of explains it a little bit. So this is about modeling dependencies. It's the example that we've run a minute ago. So you can see on the top part of the diagram what seems to be like a mobile network, right? So we see the node Bs that are connected to the controllers, and this logical connection, right, this interface, actually runs typically over an IP network, or it can use some microwave links to access remote areas. But there's some kind of underlying transport technology, and well, this is simplification, of course, but it can be many levels. They have many levels of complexity. So modeling these dependencies and then exploring them for troubleshooting and service assurance is one of our key use cases. And if we look at some names, we see that Nokia are embedding actually Neo4j in the platforms for service automation, network optimization, and dynamic assurance. We have also SFR in France. They're a mobile operator in France that are using Neo for service assurance as well, in particular for impact analysis and root cause analysis in the network. There are a few software companies, and we mentioned here Xenos and HP that are embedding Neo4j and as a backend for their OSS platform and the service assurance suites. Good. What about the BSS side of things? So BSS is basically the applications that support the more customer-facing activities, right? So things like billing, order management, CRM, call center automation, and that's a particularly interesting area. We'll talk also about revenue management and product catalog in a minute, but I'd like to talk a bit more about this incident management enterprise support, which can be considered part of the CRM. So we have a number of companies that are enhancing their incident management solutions with Neo4j, and they do it by creating what these days is being called a knowledge graph. So they're building a knowledge base, and they use it to link to tag the support tickets to topics. This tagging can be done manually, but the agent that creates the ticket adds it to the system, or it can be automated based on the description. There can be some text and entity extraction in the description of the ticket. And basically, they're connected. They're linked to topics. Topics are connected to documentation, to some useful resources, to previously solved incidents. Basically, it provides a knowledge base that helps and accelerates the resolution of the incident. So that's, yeah, as I say, it's a kind of a precursor of the knowledge graph use cases that we're seeing these days. Actually, we're going to have a webinar next week around that. And we have some very interesting customers, not only in telecoms like NASA, the space agency, and eBay, that are using Neo4j to support the knowledge graph behind the shopbot. So yeah, but as I say, we've had for years now some telco customers implementing this notion of knowledge graph for their incident management systems. And not only that, because there's also, if you think of the journey that a support ticket follows from the moment is introduced in the system, a customer calls with a problem, and the agent fills in the details, and then it's added to a queue, and then it passes through all the teams until it's solved. Analyzing this journey is generally a graph problem. So we see that customers are, and this is a very common problem that virtually all the mobile operators and telecoms operators that we've been talking to have. So as I say, they're analyzing this journey to identify patterns when, for example, a ticket is being bounced between teams, and that's delaying the resolution, or finding teams or areas where they have to be addressed in order to optimize this resolution. So this is I would say one of the interesting areas. Again, if we want to talk about some names, we have both Cisco and GCI. GCI is a regional telco that operates in Alaska, and but there are many more that are using Neo4j to enhance their enterprise support systems in the way that I've just described. StarHub, which is one of the major telcos in Singapore, are using Neo to manage the product hierarchy. So again, a product hierarchy is a rich and complex structure that can be captured in a graph in a natural way. So they're using it as a backend of the product catalog. We have also 3 in Sweden. So 3 in Sweden now are using Neo as the backend of the self-service and mobile billing portal. So the customers can check their unbilled usage, their unbilled calls, their service usage. But at the same time, 3 are using that to forecast monthly payments and to do customer segmentation. So yeah, I think that's the use cases that I've mentioned on the BSS side. I'm going to skip over orchestration probably to go straight into Internet of Things. So in Internet of Things, that's a very hot area, and we have 2 big companies there. So we have Telia in Sweden, in the Nordics, in Europe, and we have also Comcast in the US. And what they're doing, well, Telia is using Neo as the backend of their main smart home offering. It's called the Telia Zone platform. And what they build is, well, it's a Wi-Fi based cloud API that service providers, and these are partner companies approved by Telia, can develop solutions for the end users. So the platform will offer information through these API. For example, when a customer comes in the house, in the Wi-Fi zone, which is basically their home, and events, for example, when they come in, they leave, they connect through particular devices. And well, the platform was announced earlier this year, and they actually presented it at our annual conference in Europe. And they did talk about one of the first solutions that had been built by one of their partners, and it was Spotify, and it's called CoPlay. And what it does, it basically detects who's in the house by checking who's connected to the Wi-Fi and to the Wi-Fi router, and it builds, the application will build a shared playlist. That's a pretty cool idea for when you have friends at home, and it builds a shared playlist based on the preferences of the individuals in the house. So that's still, and you can see also the graph here. So it provides the context that they require, like modeling the zone, modeling the devices connected to it, the applications that run on each device. We see that a device can be used in many zones. So that's the idea that I was describing before, when a customer visits a friend or something like that. And then we have Comcast, which similarly are using Neo as the backend of the well, again, it's their smart home offering. So it's they call the XFi, the personalized Wi-Fi experience, which is backed by Neo4j in what they call the Xfinity profile graph. Sorry. Good. So compliance. I was mentioning before that I have some companies. That's not just telecoms, but we have customers in the telecoms area using Neo4j to model basically metadata, because in order to capture information, for example, about lineage, about where data is persisted, where data is stored, is critical, especially for compliance situations like GDPR, as you can see there. So what you see in the diagram is an example of vertical lineage. So this mapping of the enterprise ontology to the logical models of the different applications in your data architecture, and then ultimately to the physical storage, to where the data is actually persisted, which is extremely important. For example, being able to track where confidential information or critical information about customers is being stored. There's also the case of horizontal lineage, which is more process-based. So see how critical data elements move between systems. So being able to think of the example of some figures, some piece of information that's presented on a dashboard, being able to track what's the source of that data, which kind of transformation that data has gone through. That's something that our customers are using Neo4j for. And one good example is Orange in France again. Good. So I think that I hope that gives you a good overview of how our customers are using graphs. But I would like to to now go into a bit more detail in what a solution would look like, and I've chosen this area of network planning and service assurance. It's a long title there. I talk about this notion of cross-domain network and service topology, and by that I mean, if you think of any complex network, you will find multiple vendors, multiple technologies, which inevitably will impose multiple siloed system, because the different domains, the different areas will be managed by different systems, and having a unified view that goes across all domains is not an easy problem. But Neo4j is going to be the platform where you can precisely implement this unified view and run complex planning exercises and things like impact analysis and root cause analysis for service assurance. Let me talk a bit more about this. So what would the model look like? So first of all, we're going to need, for planning, we're going to need a route-oriented model. So we're going to need to know, for every layer in the network, know which elements connect to which other elements, in order to then be able to answer questions like, what's the most efficient path between A and B? And most efficient can be determined, that can mean shortest distance, capacity, usage. There's a number of elements that we need to take into account to solve this problem. But very particularly, if we think again of service assurance, we will want to provide redundancy, like in the case I described before. We will want to avoid single point of failure. And for that, maybe a layered view is not going to be enough. So we're going to need to know about the dependencies to avoid situations like the one I described before, when a deeper analysis is required to understand what's the implication of these cross-layer dependencies. So this model is one part of it, and that's what it can look like. So this is more for those of you who are into data modeling and want to know a bit more about the detail of it. But the graph model is has two basic building blocks. So it's nodes and relationships. The nodes represent the entities, and the relationships connection between them. And both nodes and relationships can have attributes. So here you see four network elements identified by some unique identifier here, and then we have connections that will have a type. So we'll be able to model, I don't know, SDH, pseudo-wires, any kind of technology, VLANs, any kind of connections. And we can add information like capacity, usage, anything. So this model will make it possible for us to answer questions like, we need to provide a connection between 1 and 3 of 1024 capacity. So what's the optimal path, or which are the possible paths? And if we analyze that, we'll see that it will be the one going through 2. So this is the kind of questions that we'll be able to answer in this model. But as I was saying, for some other queries, we're going to need information about dependencies. So we're going to need a multi-layer representation of these dependencies, right? And that is going to require another type of model that will look something like this. So in this case, we're modeling relationships, connections between nodes as nodes, right? So this node has a start and an endpoint, so it connects 2 nodes. And by modeling it as a relationship, as you see, it contains exactly the same information. But by modeling it as a relationship, we can now say that there's an end-to-end connection between 1 and 3, modeled by this node up here, that's carried by these are the 2 relationships, these are the 2 connections, right? That connect the 1 to 2, point to point, and 2 to 3, right? So this is kind of the dependency-oriented model. And in this kind of model, I can ask questions like, what depends on what? What would happen if this connection would go down? Which would be the nodes, which would be the logical connections on top of it that would be affected, right? And what's great about the graph is that we don't have necessarily to choose between one or the other. So we can have the 2 models coexisting in the same graph. And that's what we call a dual model in this case. So we're keeping both, actually. We're keeping the relationship representation. So if you think of the connection between a node 1 and node 2 that's represented by this relationship, it's an SDH connection. This is the capacity. This is, of course, a simple example that's made up. But we see that this connection is also modeled as a node here. So this is exactly the same connection, same information here. But we will use one or the other depending on the type of query that we want to answer. Right, and it's kind of it's a relatively frequent, it's quite a natural thing to accommodate multiple views, multiple versions of your data, sometimes redundant, to be able to answer to different types of workloads, different types of queries. So let's look at some examples. Well, before that, of course, that's what I was saying before. This kind of dual model, this kind of complexity will create graphs that are not necessarily easy to explore globally. So we will probably analyze them by layers, and of course it's possible to create more human-friendly views. And I have 3 examples here, like one produced directly in Neo4j's browser, a custom visualization that you can create yourself by using any of the visual libraries that on JavaScript, Python, anything, and or even use third-party BI tools, like it is an example of Tableau presenting data coming from Neo4j. But again, I think the most interesting use of this kind of models is on the automated side of things. So being able to issue a complex request and getting an answer in an automated way in a matter of milliseconds rather than this exploration. And that's the example that I was going to talk about. So let's think of this network. It's, made up one, but it's a network around the city of Paris, and think of the problem of connecting 2 locations to each other. So think of that as a branch of a bank connecting to the head office, or so. There's 2 parts to the problem, right? First, we have to find for each of the location which is the best point of access, right? That might be just purely geographical analysis, so we want to find which is the closest in terms of distance. But then once we've found the optimal point of access to the network, we want to find what's the optimal path across the network to reach the destination, and that's path analysis. That's planning, as I was describing it before. So what we want to find, that's the question, is what's the best, the optimal way of connecting these 2 locations through our network. And I'm going to show some cipher, but I think it's pretty intuitive. So let me explain it. So it's a 3-step process, right? And that combines actually the pure path analysis with the geospatial component, which is a component that you get with Neo4j as well. So the first step would be, let's find what's the closest. If we think of origin as the point, the latitude and longitude representing one of the locations, the one at the top, we're going to find which is the closest node in our topology, in our network topology, that we can reach in terms of distance, and that would return ON. ON would be the starting point, the point of access. We would do exactly the same on the element at the head side, the head office at the bottom. So we will do a call to our spatial component and to find the closest point to this destination. Destination again would be the latitude and longitude of the location, and we find the destination node. So now we have the 2 nodes in our topology, and all we have to do is find which is the optimal path. And here I'm using the shortest path function that comes with Neo4j. Shortest path in this case is the simplest version of shortest path analysis, and it will be measured in terms of the number of hops. I'm just trying to find which is a link of variable length, which I'm setting a limit to 5, so it won't be. That's an optional component. I can decide if there's a limit in the length of the exploration, the depth of the exploration, and that will return which is the optimal path, the shortest path. I understand that in the real world scenario, this will be probably not measured in terms of the number of hops, which is not super relevant, but it will be more measured in the capacity of the link, the cost of the links, the distance. So an algorithm like Dijkstra will be more relevant and typically the one we will use, but the concept is, I think, it's still valid. So that would return, if we run this in Neo, it would return something like this. So we would get the distance to the origin node, the ID of the origin node, and then the path to the destination, and the same at the other end, the destination node and the distance, right? So that's the structured information, but it can be presented also as a graph. So this is the actual path that connects the 2 locations. And in our visualization in Tableau, that would be, well, something like this, right? This is the path that we would come up with as the optimal connections between the two locations, right? So I think it's pretty powerful. Again, if you think of this is a complex problem that we've been able to express, to describe in 3 lines of code, and that's because we modeled the data as a graph, which is the optimal way to do it for this kind of complex topology problems. So this is the planning side of things, but we can also look at the dependency analysis. And in the dependency analysis area, I'm going to take two examples of 2 types of processes that I'd like to talk about. The first one is event prioritization. So here we're in the area of event management, alarm management. So we think of a flow of events or alarms that are coming from our network. This will be things like, loss of signal in a particular interface, a link going down, a node not responding, things like that. So if you think of that, these will come in the thousands per second, depending on the size of your network, of course. So we need to prioritize them. We need to in our NOC, be able to understand what's the impact, what's the severity of each of these failures. Some will be more relevant than others. And in case of when we need to act, we need to know where to send our engineers and in which ones to treat in order, right? So the problem is finding what's the impact and use that information based on the topology to determine which events, which alarms to deal with first, right? So this is event prioritization. There's a similar problem, which is that of event correlation. So what we want to do is take events and not consider them individually as we were doing before and just prioritize them, but rather take them together, assuming, of course, that they arrive in simultaneously in a reasonably close space of time, and understand that some of them will be related, because we see a network there's plenty of dependencies between elements in the network. A failure of one of them will have inevitably impact in others. So we don't want to treat the symptoms, we want to address the root cause. So this event correlation is more a root cause analysis problem, and what we want to do is reduce the number of alarms based on the fact that we only deal with the root causes and not with the symptoms. So these 2 problems basically involve an exploration, a deep exploration of the topologies, the dependencies in the topology. So think of that one of these events that we receive can be an interface reporting loss of signal, and what we need to do in a matter of milliseconds is being able to determine what's the ultimate impact of that failure. So we will find that there are logical channels depending on this interface failing, this link failing, and then there will be services that depend on these logical components, and these services are providing actually services to a customer that might be let's say a platinum customer, a customer for which we have a strong SLA, and we can't afford to have this service down. So we have to address it first and before others. So this topology analysis is a complex one to run, and it's something that we need to do in a matter of milliseconds, as I was describing, as the events arrive. So what does that look like with this kind of query in our model? Well, it's, I'd say, disappointingly simple, because all we have to do is identify the failing element. That will be an interface, that will be a link, that will be a node, that will be a card, and then from there on, just traverse the dependency chain. So be able to explore which things depend on this failing element, and this dependency will be direct or indirect. That's again what the asterisk represents. So we will ultimately end up reaching services, and these services will have priorities. So let's think in our simplified example that services have a priority of 0, 1, 2, and 3. And what we can do as a simple way of dealing with this to compute the severity of an impact is take the maximum of the priority of the services affected by it. If you think of the result of this stock pattern, this is going to be a tree. So there's going to be a number of elements depending on this link going down, and these ultimately, this tree will have as leaves, as terminal element services. So if we take the worst case, we'll take the maximum of the priorities of the services affected, and we can use that as the severity of the impact, right? So if we have at least the one severity 3, the priority 3 service affected, we will set the severity to that value. So again, this kind of query is run super efficiently in a graph database like Neo4j, and what I'm going to do is analyze how does that behave at scale, because as I was describing before, we're going to get these by thousands per second, right? So this is high volume of events coming from a network. So we want to be able to understand what's the behavior of these in at scale, basically in a large network. So my first experiment was based on a small graph, it's still a real network, but it was relatively small in terms of nodes and relationships, because it was around 1,000. And the average depth of the dependencies was 5. So there were up to 5 layers of dependency that I needed to traverse whenever an alarm or an event arrived. Still, this is the output of a simulation tool that I run. This simulation was based on starting, 128 clients that were issuing synchronous requests to the database, to Neo4j, basically sending alarms of elements failing, and just with a small wait of 1 millisecond between requests. Basically, it's synchronous requests, so the client will not send the next request until the server has returned with the result. So in this scenario, by running this for a minute, I got to process approximately a million requests, and you see the numbers here. So approximately 16,000, a bit more than 16,450, 16,000 per second. Requests per second, and the average, well, the mean response time was 7 milliseconds, so single-digit millisecond processing. That's pretty cool, I would say. But that was on a small graph. So I was asking myself what would happen in a, kind of knew the answer, but I thought I'd test it. So what would happen in a much larger network? So not like 10 times, 50 times bigger, but what about 50,000 times bigger, like 50 million nodes in my graph? Now the average depth goes up to 6, but quite surprisingly, we see that the mean response time is hardly changing. So it goes to 8 milliseconds. The mean the mean number of requests per second goes down to 14,000. And what does that mean? Well, it means that I've highlighted it before to make it easier to follow, right? So that's the impact. So that means that a 50,000 times increase in the size of the data set has such a small impact on the query performance, just 0.14. So if you think of it, we could easily consider that constant performance, and that's one of the characteristics of native graph databases. So Neo4j, the native graph nature of Neo4j. Let me explain a little bit what that means. So what we mean by graph native is that we persist the connections between data points. So we don't need to run, we don't need to work out the connection between data points by running an index scan, by doing joins like we were doing in the example at the beginning. So the connections are explicit. So what we're doing when we traverse a graph is we're chasing pointers. We're exploring graph in a very efficient way. This pointer chasing exercise is something that computers do in a very efficient manner, as opposed to having to scan indexes every time we do a self join to traverse these dependencies. So one of the consequences of this native storage and processing and this persistence of connections is that the performance of queries like the one I'm showing here on the screen will not be affected by the overall size of the graph, and that's crucial because that makes them predictable. So they're only affected by the portion of the graph that they traverse, that they explore. So if you think of a table in a relational model that goes from 1,000 to 50 million, you will definitely see an impact every time you scan it to run a join. That's not the case in a graph, as you can see in this example. So a significant increase like the one you're seeing here will not have an impact in the performance, or barely noticeable, and that makes this way of storing, this type of stores, adequate for this kind of processing where predictability is key. So we need to understand that at a large scale the performance is not going to be degraded. So, well, I hope that has given you an overview both of the use cases, how our customers, how graphs are being used in the telco industry, and also an idea of with a bit more detail of what a solution can look like. So I'm going to stop here and probably open it for questions.
Great, thanks, Jesus. So we have a bit of time left, and we'll go ahead and take as many questions as we can. So just a reminder, you can add those into your GoToWebinar questions panel. All right. So we have one here. If you go back to your slide 24 as an example, are you able to share kind of the best practices on how to model transport here? So for example, is it better to label the link between two routers with an identifier, or would it be better to create an extra node between them with properties? And what are the benefits of trade-offs of making kind of all the nodes versus the intuitive simplicity of just connecting them between?
Right, that's a great question, and I think it probably came before I I explained this dual model, because the great thing with the graph is that you don't have to choose one or the other, so both can coexist in a natural way, as I've described here. So, for example, if you're doing a path analysis, if you're doing a shortest path, trying to answer a shortest path question, you will benefit from the relationship representation of that connection. But if you're doing dependency analysis, you will probably want to use the representation as a node. So some will have advantages and disadvantages depending on the use case, but the good thing is that you can have them coexist in the graph and use one or the other depending on the case. So that's a great characteristic of a graph. So you can keep adding layers and enriching your graph in a way that you can deal with different types of throughputs. I mean, different types of workloads and different types of queries.
Great. And are you able to discuss how to model hierarchies? So how are R trees? Would they help with this kind of hierarchical nested modeling? And is there really any formal inclusion of that in Neo4j, or is it up to the individual as a modeler to implement it?
Yes, well, I think the answer is yes. I mean, it's up to the modeler to. I mean, the label property graph that Neo4j implements is very basic, but still very powerful and very expressive. And it just it's based on nodes and relationships. So this can be used, of course, to model trees, as you describe, or the question describes. But it's up to the modeler to use it and to represent it. And as I say, nodes, relationships, properties on them. You can use labels as well. But it's it's a modeling exercise, I would say.
Okay. Let's see here. And how would you model our network link changes? So if you wanted to query the history of a node, what would be the best way?
Right. So this is also a very good question, and it's not an easy one. So if here the answer is it depends on the kind of requirement. So one thing you can do, of course, is keep snapshot of your network. I mean, you can. It depends if you need these changes. I mean, these different versions online to be able to query cross versions, or to query across time versions of your topology. If all you need is be able to track what your network was like, let's say a week ago, a month ago, to troubleshoot, to do some forensic analysis, that can be done by just saving, doing a backup, if you want, of a timed backup of your graph. But if you want to keep it online, there's a number of ways in which you can do that, and there are some best practices that will take a bit too long here to explain. But you can use things like, use chained versions, like applying the time trees or chained links. It will be, I would say, I would treat it in a case-by-case basis and understand what the requirements are, because if you see here, adding an extra dimension can even make the model a lot more complicated. So we have the single layer connectivity, we have the cross-layer dependency, and adding a time component can really complicate things. But still, there are ways to do that, and well, we can probably take that offline. So feel free to reach out, and we can discuss best practice around that.
Okay, so then if you wanted to visualize that over a timeline, it seems like you would need to implement the hierarchical view with separate UI views into the graph, or would it be just one graph with multiple views via the UI? Yeah,
well, the whole visualization of network topologies is a tricky one, and I was showing some examples before. So you probably want to analyze them by layers, something like what you see in these three diagrams. So that does not take into account I mean the underlying layers for each one of them. Again, if you have time, this is more kind of an interface design than, I mean, you can model this complexity from the data point of view, so you will be able to represent it in the graph, you will be able to query it. Now, in terms of presenting it, that's more of a design exercise than a data problem, I would say.